This is the solution to the second question from the revision worksheet on inferential statistics. So in part A, we're talking about a health clinic where we've got waiting times normally distributed with a mean of 34 and standard deviation of 8. Let's just note these values first of all. And we're trying to figure out the chances that somebody will wait between 30 and 40 minutes before being seen by a doctor. So again, drawing a quick sketch will help us visualize this. So we want to figure out what is contained between 30 and 40 minutes as a proportion of the overall patient population. So we first of all need to figure out what Z values are associated with the 30 and the 40. So this is our straightforward x minus mu over sigma formula, because again, the 30 and 40 minutes aren't average waiting times, they're just individual waiting times. So using that formula on the 30, we get minus 0.5. And using it on the 40, we get 0.75. Remember, I can't look up negative Z values in the log tables. I can look up the positive versions of them. But if I look up the positive version of 0.5, what it's going to give me is the entire area to the left of 0.5 or to the right of minus 0.5. And that's 0.6915. So really what would be handy for me is if I could work out this region here to the left of minus 0.5, then work out what's to the left of 0.75 and subtract those. So I can find this little red shaded area by just taking 0.6915 from 1, which gives 0.3085. And then I can look up directly what's to the left of 0.75, and that's 0.7734. Now that's everything to the left of that guy, but I only want to go as far as this 30 or the Z1 equals minus 0.5, so I don't want this bit in red. That's that guy there, the 0.3085. So I'll just subtract it, and that will give me what's in between the two. And that gives me 0.4649. In part 2, they ask you to find the upper quartile of waiting times. Now, quartiles are quarters. So if I think about the bottom being 0 and the top being 1, and then I've got 0.25 up as far as here and 0.75 up as far as here, then this is the location of the upper quartile. Sometimes this gets called Q3 because it's 3/4 of the way up. Visualizing this in relation to a normal distribution, I want to figure out at what point I've covered 75% of the area underneath the normal distribution. So the 75% or 0.75 refers to the area. So I'm going to look up a Z value based on that. I'm going to go to my log tables and I'm going to find the closest Z value or the Z value that will give me the value closest to 0.75. And in this case, that is Z equals 0.67. Now, the question doesn't ask me for the Z value, it asks me for the waiting time. So I have to work out the X. I'm going to have to use the Z formula for this. So let's just remind ourselves that mu is 34 and sigma is 8. Let's remind ourselves of the formula, X minus mu over sigma. And I can fill those values in and then manipulate to get X. And my answer is 39.36 minutes. So on to part B then. The director of the clinic wants to check if these times are accurate. Now, when they say these times, it means we're going to be able to refer back to information earlier in the question. So there's a sample taken of 100 patients. Let's make a note so that n equals 100. We're told this group have a mean of 35.7. And the standard deviation is the same as before. Now again, I've called this S because we're talking about a sample, but in effect, you're going to deal with this as sigma because S can sub in for sigma. Okay, so what do they want us to figure out then? They're saying test the hypothesis at the 5% level of significance that the mean waiting time for the patients has not changed. State the null hypothesis and the alternate hypothesis, and then give your conclusion in the context of the question. So let's state our hypotheses. The null hypothesis is that the mean hasn't changed, and the alternative will be that it has. So in the previous video, I used a confidence interval to test my hypothesis. This time I'm going to do the statistic, so test statistic, the Z value, just for a bit of variety. So when I'm working out my Z value this time, just bear in mind that I'm talking about means the whole way around here. I'm testing the value of a particular mean. My sample, I've got a mean for as well. So it's going to be the Z formula with all the means in it, X bar and mu. So I can fill in my values and I get 2.13. Again, with Z values, always run out off to 2 places of decimals because that's all you can look up in the log tables anyway. And this value is my test statistic. Sometimes they'll specifically ask for this in the question by name, so it's important to know what they're talking about. Now that I have this statistic, I'm going to be able to draw my conclusions. So This is important in relation to the 95% confidence interval. Now, the 95% confidence interval's limits are defined by Z being minus 1.96 and plus 1.96. So what I'm really interested in is whether this is within those margins or outside of them. Clearly, in this particular scenario, 2.13 is definitely outside of that. So I'm going to state the obvious thing, first of all, that 2.13 is greater than 1.96. So this tells me that the result is significant. So the result is significant basically means that my null hypothesis is dodge. So I'm going to reject HO because there is evidence to suggest that the mean wait time differs from 34 minutes. And we're on to part 2. They want us to find the p-value of the test. Now, what's handy about having done the test statistic in the previous part of the question and not just the confidence interval is that the test statistic is actually a calculation that you need to get the p-value. So straight away, I'm going to write that down. So Z is 2.13. So what I'm trying to figure out now is what are the chances of being that far away from 34 if 34 was in fact the mean? And I don't just talk about being that far away on one side, but overall. So how much space is getting taken up out here and out here? So I'm going to first of all figure out the probability of being below 2.13, this region, and then I'll take that from 1 to get one end of the shaded area. So that gives me 0.9834. And then I want to figure out this guy here. So I'll take that from 1, which is 0.0166, and then I'm going to have to double it to get both ends. And once I get both those shaded ends of my diagram, that's my p-value. So now onto the explanation part. So the first thing is to make a statement about what the p-value actually tells us. And the most obvious thing we can say is that this is less than 0.05, and that was kind of referring directly to the 5% level of significance. So basically there's a really small chance of this happening. It's about 3 and a bit percent. The reason there's such a small chance of this happening, that's what kind of leads us then to reject our null hypothesis. So what can we say? And of course, we're bringing in some context here. So we're talking about the times and the weighting. So there's a 0.0332 chance, that should say, that, or probability if you like, that 34 minutes is an accurate mean wait time given the wait time of the sample. I'm afraid dinner is ready, so I'm going to have to come back and do part C and part D a little bit later on in a separate video.